For this year's science project, I intended to try something related to my hobby, which is music. After going through quite a lot of projects, I attempted an experiment that is on the phenomenon called spontaneous synchronization. That was just a demo, and for the actual experiment, I want to measure the number of metronomes and the time it takes to get to spontaneous synchronization. Hypothesis: if the number of metronome increases, then the time it takes will decrease. Procedure: put the foam board on top of the two horizontally placed soda cans. Put the metronome on top of the board. Set up the mic and connect it to my DAW. There will be 3 test cases in this experiment: 3 metronomes, 4 metronomes, 5 metronomes. First, let all the metronomes except for 1 synchronize. On the offbeat of the synchronized metronomes, release the metronome that is at rest. I specify the time of release so that in every case, the release time is roughly the same. Initially, I did not consider this factor, but after a few trials, I realized this is actually a confounding variable that will contribute to false experimental results. So I controlled it by defining every experiment to be released on the backbeat. Using a video camera, I shall record the entire process, and finally I will import the footages into iMovie, where I cut the moment from the moment I release the last metronome and the moment where all the metronomes are finally synchronized. The resulting time is the time needed for synchronization. Meanwhile, I will also use my mic to capture audio from my computer, which will give further insights into the experiment and the phenomenon of metronome synchronization. So here we are in iMovie. You can see 3 separate projects corresponding to the number of metronomes that are included in the test cases. Clicking into the one experiment that has 3 metronomes, you can see all of the videos that are cut and ready for analyzation. So they're cut from the time of release, as you can see, and all the way till the point where synchronization is achieved. So here are the experimental results. I plotted the data, calculated the mean and standard deviation, which helped me to complete 2 t-tests. The t-tests have given me statistically significant evidence to illustrate that 3 metronomes take far longer time than 4 metronomes to reach spontaneous synchronization, and similarly 4 takes much longer than 5 metronomes to reach spontaneous synchronization, which directly and strongly supported my original hypothesis. Unexpectedly, the audio waveform actually provided something that videos alone could not prove. So initially I set all the metronomes to close to 208 BPM. And here in this audio workstation, I also set it, the beats per minute of the project into 208. And if I take a slice of the audio sample and drag it to the corresponding grid, what we can see is that the general shape of the peaks when everything is synchronized is actually pretty much aligned with the grid of the DAW. What that meant is that the synchronized BPM of all of the metronome is actually exactly the same when they first started out, which is also 280 BPM. So the phenomenon of spontaneous synchronization, as I would explain it, would be the remarkable effect in which individual things that are originally changing at different rhythms starts to, over time, change in the same rhythm due to weak interactions with each other. Now, what is even more interesting is the phenomenon happens throughout the universe, not only in physics, but also in biology and chemistry. For example, in the animal world, groups of Southeast Asian fireflies provided a spectacular example of synchronization. Thousands of fireflies congregate in trees at night and flash on and off in unison. When they first arrive, their flickers are uncoordinated. But as the night goes on, they build up rhythm until eventually the whole group of fireflies pulsate in silent concert. Or say the human heart, where thousands of neurons have to fire up in synchronized fashion in order to create a pump that could circulate the blood around the human body. And what is even more beautiful is in chemistry, where self-oscillating reactions such as the BZ reactions demonstrate spontaneously synchronized waves and turbulences. The patterns are truly a work of art. These are just a few examples of synchronization in our world. The possibility of further research in nearly any aspect is limitless.